Yeah, we're live. Welcome from my side to this first session in the room today. This is a Spring Framework session, and literally it'll be very core framework centric, since I'm basically talking about my current work. I serve as the Spring Framework project lead, so I'm the lead of everything up on github.com, Spring-projects, Spring-framework. The entire core framework, from the core container to WebMVC and what is now known as Webflux, is all under this umbrella. So this opportunity today is quite timely. Spring Framework 5.0 has already been out for several, for like the better part of a year already, and we are already moving towards Spring Framework 5.1. So this is very thematic. We're going to talk about everything that is really driving the entire Spring Framework 5 generation. I will also be talking a little bit about things that we don't mention that often, but that we should be mentioning more often. These are the hidden gems mentioned in the subtitle here. So we're going to talk about a few things, 3 parts. I'll get to that in a moment. This is the fact sheet. Let's just take it for what it is. This is the Spring Framework 5.0 release in last September. A few essentials summarized here. We won't actually be referring back to them, so this is the only opportunity. Spring Framework 5 is finally JDK 8 baseline, so it's everything both at the surface of the framework and within the framework's code base is now Java 8 baseline, making use of Java 8 language features, making use of Java 8 API features. Finally, this is not actually that big a deal in practice for application development purposes, because Spring Framework 4, Spring Framework 4.3 in particular, is already very much adapting to your use of Java 8, right? So this is actually more internal than application facing. For all practical purposes, if you're using Spring Framework 4.3 on Java 8, it already feels like a Java 8 based framework to you for almost all purposes. This is finally now catching up within the heart of the framework, within the core code base itself. More importantly, it's also forward-looking. It's got co-released with JDK 9, so it's already very much prepared to JDK 9's conventions, both at the API level, in terms of modularization, some conventions that are just different from Java 8, even when you're running on the class path. And we're all also embracing the latest level of common enterprise specifications out there. Basically the Java EE8 API level also got released late last year. That would be Servlet 4.0, Bean Validation 2.0, JPA 2.2 as recently implemented in Hibernate 5.3, for example. So this is essentially our new baseline. It's a very, it's almost an aggressive upgrade from our end. We always tend to be very backwards compatible with the past, but we found Java 8 as an ideal baseline. It allows us to do many things. Also at the API level, we are ready to provide lots of Java 8 based goodness in further Spring Framework 5 feature releases now. So much for really the basics, right? The focus that I have for you today in this presentation is largely in those 3 categories. It's the component style, which is the notion of annotation-based versus programmatic use of the framework. The focus on reactive architectures is, well, everything we're doing in the reactive stream space, mostly about Spring Webflux, of course. And with a little bit of time left towards the end, I'm going to quickly run you through a selection of little things that we don't talk about that often, but that should also be mentioned and doesn't really fall into the major categories. This is probably what you have in mind when you think about the Spring Component model. In recent years, we've invested lots and lots of time and energy and smarts into the annotation-based component model. We've been refining it, in particular in the Spring Framework 4 generation. Even Spring Framework 4.1, 4.2, 4.3 brought lots of refinements to this annotation-based model. It was simply the theme of the Spring Framework 4 generation. So there's a couple of things indicated here: the use of stereotypes on top, the at service annotation, the use of annotations to indicate kind of service guarantees, service qualities from the container, like at lazy. There's at transactional as a declarative annotation that allows you to tap into a middleware setup, like a transaction manager, beginning the transaction before we enter and committing it or rolling it back after we return from that method. There's dependency injection, of course, and this commented out part is already a very recent feature. This is the add auto-wide annotation on a constructor, and as of Spring Framework 4.3, if you only have a single constructor that is clearly designed for dependency injection purposes, even within the annotation-based model, we don't insist on the annotation being there. But this is also part of the annotation-based story. Those annotations really demarcate certain characteristics, indicate certain characteristics at the source code level. So this annotation tells you something about the method. That update book is a transactional method. This constructor is auto-wired. My book admin service is a lazy service class, right? So it's quite readable. And even if some of those annotations might not be technically necessary in the source code, they add to the readability of this piece of source code. So this is the essence of our annotation-based model, and it has many little flavors. This is, for example, our composable annotation model. In this example, we build a custom MyService annotation. MyService is a annotation that is being declared in your source code, in the annotations, in the applications code base, and it combines a few standard Spring annotations, common Spring annotations, onto one single custom annotation, and every time you're saying add my service, you're really combining the characteristics above in a sweet, simple shortcut with a custom name. Right? So it's the annotation-based model is very descriptive. And my service might not be the ideal name, but choose a good name, right? Order service, account service, a vertical or horizontal slice of your application that you can name this after. So annotations really have a lot of power in terms of enabling you to fine-tune the readability of your source code that way. Configuration classes, of course, very commonly used within that model, in particular in Spring Boot. This is essentially the core container features that Spring Boot is based on, where Spring Boot is really taking configuration classes to the maximum level. Configuration classes are part of the Spring component model. They are essentially components that expose other components through factory methods. And those at-bean annotated factory methods are a quite essential piece of the puzzle for any non-trivial code, anything that we can't simply call a constructor for on the target class itself. A factory method is an easy and straightforward way out, and in many applications you'll define almost all components through factory methods, even ones where you simply call new on would be return new and the class, and it's still quite readable. The model is heavily based on the annotation-based characteristics and on, of course, reflection. Every time the container needs a new instance of those beans, it's going to dispatch a call to that factory method. Behind all of this, there is a core container arrangement that is not actually annotation-based. The core container underneath is in charge of the life cycle of your components, and it's also kind of managing some configuration aspects of it, but it's not annotation-based at the heart of it. The annotation-based model is one perspective, one kind of personality of the core container that sits on top of the underlying core container architecture. And a quick forward look to our reactive architectures topic. This is the annotation-based Spring MVC model. Spring MVC is also actually not annotation-based at the heart of it, but this is the common usage model, part of the component model overall, usually a controller stereotype on top, and mapping annotations that allow you to dispatch servlet request invocations to annotated handler methods, as we call them, with a very flexible signature. The mapping, kind of the predicate that needs to match in order to enter this method, expressed through an annotation, and a very flexible signature. So if you need like a path variable, just flexibly declare that path variable as a handler method parameter. You get automatic resolution from the parameter name and automatic conversion to the parameters type. So there's many little features and special characteristics of the annotation-based model that are really quite unique to it. Nonetheless, in Spring Framework 5, we took a step back, like quite literally. We have a very comprehensive annotation-based story that kind of reached a natural point of conclusion in Spring Framework 4.3. This is still very much the mainstream usage model for Spring Framework 5. So to be very clear about this, the annotation-based model is of course the mainstream, a very important first-class citizen on Spring Framework 5 and higher. At the same time, we allowed ourselves to explore a different usage model. Like literally taking a step back, revisiting the core container, the core container's contracts, the APIs, even many of its internal optimizations, and trying to expose them to a different challenge, like purely programmatic usage. Programmatic registration of beans, no annotations involved, no class path scanning, which is easy to do even with annotations to not use class path scanning, but no annotations, no class path scanning, and even avoiding reflection. So as a kind of design goal, creating a reasonably complete setup, in particular for smaller services, for example, in the microservice architecture, where only certain beans have to be registered and a number of endpoints has to be registered, and setting it up without any use of runtime reflection, or at least allowing for it. As a major driver, we also have Kotlin, the Kotlin language. So this is primarily about Java 8. Of course, Java 8 is our mainstream reference language for everything here. So exploring Java 8's language power and exposing some of that Java 8 language power through our core contracts. But at the same time, also allowing for Kotlin, for a very idiomatic Kotlin development experience. So if you chose to use Kotlin with Spring Framework 5, then Spring should feel like a natural citizen of your stack, right? So we go the extra mile towards Kotlin support. We'll see that in a moment. What is this essentially about? And there's many little things to it, but the essence of it all is to be found at the core container level. There's this class called generic application context, actually a quite old class that was always very metadata based. So Spring internally has this bean definition model, which is essentially a programmatic metadata representation for how to manage this bean. Generic application context always allowed you to provide custom bean definition metadata. But this is sort of a little inconvenient. It's not really meant for immediate consumption. It's more for tools to use that facility. So as of Spring Framework 5, we have some very immediate methods on there that are meant for direct programmatic consumption. Those are essentially flavors of register bean. Register bean, in the simplest form, takes a bean class and creates a bean definition out of it with some programmatic default conventions. If your starting point is generic application context, there's literally no annotation processing going on. The annotation processes are not even registered. So we're not spending a single CPU cycle looking for any bean definition annotations here. The register bean footed class is simple, right? We have to kind of have a default convention, which is usually the default constructor to be called there. There's no annotation-based resolution, so no add-auto-wired resolution. It gets a little more interesting with these variants down here. This is essentially the functional equivalent of an add-bean method in a configuration class, of a factory method. But it's not a factory method, it's a sort of factory function. We actually call it an instance supplier, because technically this is a Java util function supplier. Every time the container decides to create a new instance of this bean, it's going to call this instance supplier function, which is expressed through an inline lambda expression here. So this is Java 8 lambda expressions in action. And it gets a little more sophisticated down here, where, for example, this variant here says, let's register bar.class, let's have an instance supplier for bar that calls this bar constructor as above with calling back into the context for retrieving an instance of food that needs to be injected there. So this is basically the programmatic equivalent of dependency injection, but it's very explicit. You programmatically call the constructor, you call back to the container for resolution purposes of that dependency, and it's still a regular instance supplier as a lambda expression. This is also something where lots of refining is going on still. So in Spring Framework 5.1, we intend to have a very flexible sort of collection stream style retrieval API where you can be much more sophisticated than just saying I want the default instance for foo, where you could add further characteristics that you expect from this class, and it's then resolved into a single unique instance for you. But for simple purposes, this is perfectly fine already. And there's also one more embedded lambda expression here. This is what we call a bean definition customizer, and there may be any number of those because it's actually a bar arc. So this is an instance supplier argument, the bean definition customizer. Before we actually register the underlying metadata representation, you get a callback. It allows you, or any number of callbacks, it allows you to fine-tune the characteristics. For example, setting lazy init to true, which is the equivalent of add lazy, in a quite sweet embedded lambda expression arrangement that for an innumerable number of beans, just if you have like 5, 10, 15 classes to register, this may actually still fit on a single screen and still be quite expressive, easily trackable, direct references to your configuration artifacts. There's even a little optimization over here. Why would you do this, right? I mean, we just set foo class up there. This is also an instance supplier. The sweet part about Java 8's language design is that lambda expressions and method references can be so easily bound to the same API signatures. So this is the same signature. It's a Java util function supplier, but we bind a Java 8 method reference to it, and foo : new is a reference to the default constructor of foo. So why would you want to do this, right? Why not just simply do it like up here? Well, this is a direct invoke dynamic dispatch to that constructor, which means whenever we need to create a new instance of that bean, we are going to dispatch straight to the constructor. There's no reflection involved. Whereas class.newInstance effectively is reflection. There's literally no reflection in the construction algorithm here. It's of course an optimization, right? This is a sort of extreme perspective that we take. A very pure, programmatic, functionally styled perspective. In practice, there are many shades of gray in between, right? As indicated here, you can choose to start with the annotation configuration setup. You can programmatically register beans, but use add transactional on them. You can programmatically register beans and use other annotation-based features on them. There's lots of mixing and matching. But from a framework design perspective, we try to be very clean in the sense of allowing for a pure programmatic functional style setup as well. And to kind of complete this little impression here of what we do at co-container level, this is the Kotlin equivalent. I won't be spending too much time with Kotlin, but just a few essential points. This is the same code, or variants of the same code anyway. So we are starting with our generic application context. We're registering foo class with default conventions, or we're registering bar.class with an instance supplier. But it's somewhat different, right? So where's the bar.class argument here? Here we said bar.class, and here's the new instance. And here all we have is kind of this Kotlin function that creates a bar instance. That's exactly why it is a Kotlin function. And our Kotlin extensions at generic application context level make use of overloads introduced through Kotlin extensions that register bean actually takes a Kotlin function here. And we use the Kotlin reflection API to infer the return type from that function. Java 8 Lambda expressions, unfortunately, do not allow for reflection of return types of generics. So we can't reliably infer what an instance supplier actually creates. We can't infer at runtime that this creates a bar instance by Java 8 language design. Whereas in Kotlin's language design, Kotlin functions have a reliable reflection API from extra metadata in the class file. So we know that this creates a bar argument. We don't have to repeat bar.class anywhere. And in a pure function setup, we actually call Kotlin idiomatic pure functions allow you to have a kind of it parameter that comes into the function. So calling back to the application context is also very straightforward and very pure in this setup because the application context comes into the function as an argument. This is what I'm dubbing the Java style of using Kotlin here. This is slightly more advanced. It's the same code, but using different Kotlin language features to get a bit more of a DSL style impression. It's called Gradle style usage here, just because the Gradle build tool has a Kotlin DSL that is sort of similar to this in style. But it's essentially doing the same thing. It's nesting the calls to register bean, and it's using Kotlin's refi generics to infer the types. So you're not even passing an argument in foo.class. You're generically specifying a foo type, and we can reliably infer through Kotlin reflection APIs that you mean the foo type, so you can have an even more concise expression of types here, which can be really nice, in particular in a DSL style setup. And there's several variants of this. This is the heart of this is the essence of what we're doing. There's actually more to it. We have a Kotlin bean definition DSL that's shining up in some recent efforts. So there's actually quite a few flavors. And this is essentially what we're doing here. We're trying to take Java 8 as a language, Kotlin as a language, try to take their language features and idiomatically expose them, idiomatically support them in the best possible fashion in our own API design, so that the framework can be a natural citizen, a natural companion to Java 8 and Kotlin language features. Let's move on to reactive architectures, which is sort of connected. In Spring Framework 5, we also took a step back in terms of web architectures. Historically, in the Java ecosystem, we are always building on the servlet API. Not only on the servlet API, we're building on the servlet invocation model. A servlet container with a large thread pool, like 150 or 200 threads in it, and every time a request comes in, you kind of own a thread. You get a thread out of the thread pool, you process the request until you arrive at the complete response, and then the thread goes back into the pool. This invocation model is common to all servlet-based web frameworks, and in particular, common to Spring MVC, which is very much a servlet-based and servlet-exposing web framework. Now, for a different challenge, we kind of put servlets to the background for a moment and focus on a different interaction model. Reactive Streams, the Reactive Streams initiative on reactivestreams.org provided a perfect solution, modeling a very essential part of stream interaction underneath the covers for us. So this is essentially a small kind of SPI style, very minimal arrangement, just a few types coming in the org Reactive Streams package. They are implemented and kind of used at a slightly lower level. You wouldn't code at that level, but the underlying architecture, your web server, your data store driver, your web client API might use reactive streams underneath the covers in order to efficiently interact with each other. The basic idea is very simple. It's an asynchronous interaction model with a flow control model. A publisher is able to produce data, to produce elements of data, but it's not actually doing anything until a subscriber is being registered, and the subscriber is in charge of flow control. It asks the publisher for further data as the subscriber can process it and pass it on. If the subscriber could be, for example, an HTTP response stream. If there's currently network suggestion, it's not going to do anything. It's not going to ask the publisher to produce any data. So the publisher is not just pumping data to the subscriber, it's reacting to the subscriber's take calls. So it's a very flexible model, allowing for very efficient use of both threading resources and memory resources and buffers at runtime, modeling a problem that typically emerges in rather extreme scenarios. So for very high loads, very uneven loads on web servers, you're going to run into a situation where the servlet model is suboptimal, right? Where you might exhaust your thread pool, where you might start rejecting some incoming HTTP requests simply because there's no thread available to process them. In a reactive streams architecture, in an ideal scenario, you'll have an event loop underneath the covers. It's totally asynchronous and totally non-blocking, modeling the flow control in the form of back pressure here, and an event loop just having as many threads as you have CPU cores, processing all incoming requests. No single request owns a thread. We only kind of grab a thread from the event loop, sort of, if we're actually ready to process an element. Otherwise, incoming requests and their publishers and subscribers only occupy a little bit of memory. They're going to be called back from the event loop whenever needed. This can scale to a very high level, and it can scale very efficiently and reliably. To the best possible degree. It's a different way of consuming and exposing your hardware resources, your operating system resources, your network stack to the application. The way that we are integrating this into the core Spring Web architecture arrangement is through a parallel web framework. We have the traditional Spring MVC on the servlet API on a servlet container. In Spring Framework 5, we literally introduced a new web framework that sits next to it. This is the Spring Web MVC module, this is the Spring WebFlux module, so it's even a separate jar. Spring WebFlux over there is not based on the servlet API, it's based on Reactive Streams and on our own project Reactor as a Reactive Streams implementation, as a kind of kernel for processing Reactive Streams, and a custom web abstraction that we have on top of it. The servlet model is fundamentally blocking, right? You get a thread assigned to you, that's one thing, but you also interact with servlet input streams and servlet output streams, blocking I/O interaction. If there's network suggestions, then output stream write calls are going to simply block. That's why you need a dedicated thread. You might actually block at any point the thread that you own. Here it's an event loop-based, totally non-blocking architecture on Reactive Streams. It needs to be non-blocking. Don't ever block a thread in an event loop. I mean, if you've ever done user interface programming, you can kind of see what happens when you block the rendering thread, right? It's a similar model over here. This allows for blocking APIs. You can call blocking APIs here. You must not ever call a blocking API over here. So it's really a fundamentally different architecture that is being designed here. Now, one interesting little twist. We have server containers underneath. Very common Tomcat, also very common Chetty, or of course Wildfly, whatever's to be found underneath here, any server container. A design goal here was to support NetT, this asynchronous networking stack, the most powerful networking stack we have on the JVM. So Spring WebFlux can run on NetT and sort of runs on NetT by default, at least in Spring Boot. Alternatively, you may also adapt other HTTP kernels here. So you can use Spring WebFlux with an event loop arrangement on, say, on Tomcat or on Chetty. But Tomcat and Chetty are not being used as servlet containers here. Their servlet nature doesn't shine through. They are reduced to the essence of what they are doing. They are HTTP servers, HTTP kernels, and we adapt our Reactive Streams abstraction on top of their HTTP processing functionality. So this is not the same Tomcat and Chetty as you know it. It kind of shares a lot of the configuration, but it's used in a different fashion, not as a server container, rather as a reactively enabled HTTP server. This also comes back to us here that Spring MVC and Spring Web Flux actually share quite a few things, but they are also different in many ways. So Spring MVC is the servlet-based architecture, Spring Web Flux is reactive. That already implies lots of things. Blocking APIs like JDBC, JPA, REST template, any kind of blocking calls can only really safely happen over here. Here it's an event loop setup, totally non-blocking. It can run on Netty. It has a programmatic registration model, which servlets don't have. Servlets are sort of a more declarative affair these days and a more like discovery-based affair. But there's also some similarity. We try to abstract as much as possible to be found in Spring Framework 5's Spring Web module, where the annotation-based model reuses the same annotation types. There's a strong degree of similarity. We have a Reactive Client API that is primarily designed for use in Spring Web Flux, of course, a sort of modern-day alternative to REST template, but it can also be used in traditional Spring MVC. And as mentioned, you can choose to use Tomcat Jetty, or in particular Undertow. You can choose to use them as servlet containers in Spring MVC or as reactive HTTP servers over here. Undertow is actually a fine example here because Undertow is the HTTP server underneath Wildfly, and it comes as Undertow core and Undertow servlet sitting on top of Undertow core. Here you need Undertow servlet, here you only need Undertow core. So Undertow has a very strict separation between its servlet-based and non-servlet-based usage models. So let's look at some code again, just to illustrate the programming model that comes with this. This is a reactive web controller with reactive endpoints. Initially, it might appear to be just a Spring MVC controller, but if you look a little more closely, it's reusing the same structure, it's reusing the same annotations. It still has mapping predicates here, it has flexible argument signatures, everything basically as we know it. But then, what are those handler methods here actually doing? They are not getting an incoming request and trying to process it. They are rather getting a dispatch for an incoming request, and they are meant to build a Reactive Streams publisher for each such incoming request. So if we get this call coming in here, we basically know that we are not in a position to process the request. We are building a step of processing, basically an arrangement that is capable of producing an HTTP response for this request. What we have here are both implementations of Reactive Streams Publisher, of the publisher interface. Those two are higher level APIs that we suggest for the programming model. This is, they both come out of Project Reactor. This is a representation of a single element or none, a sort of Java util optional for Reactive Streams. And Flux is a stream of elements, potentially even unbounded. It's a sort of Java util stream for Reactive Streams, right? Both of them are Reactive Streams publishers. The runtime system for an incoming request just calls, according to the mapping predicate, those handler methods. The handler methods builds the publisher, this pipeline, this processing pipeline for us, immediately returns it, and the runtime web stack then kind of calls this publisher from its event loop whenever we are ready to trigger the next step. So it's a different purpose. This is syntactically similar, but semantically quite different. Reactive Streams-based handler methods are to be called back at a later point. The handler method itself just builds this arrangement of steps in order to arrive at a response. There is some degree of flexibility here, right? I mean, you have the signatures, but you also have the ability to declare an element type. There's a reactive codec model. So if we have a user object, like a data class here, that is being returned, we send it through a codec arrangement for JSON returns, for JSON content types or for XML content types. We have default codec implementations based on Jackson and based on ALT, so being capable of rendering those out in an asynchronous fashion. So for each individual element, there's also an asynchronous rendering model that applies to them. So this is essentially the programming model. These annotation-based web controllers can run on a pure Webflux stack, so they can run in a Webflux server arrangement on Netty with an event loop setup. In such an arrangement, a pure reactive server stack, all your web controllers need to comply to this programming model. All of them need to return Reactive Streams publishers. So there is a pure version of doing this. At the same time, you can also take a reactive web controller and deploy it to Spring MVC on a dispatcher servlet because it's part of the programming model. Now, what would happen then? Right? You code your controller like this, then you take it and deploy it to a Spring MVC arrangement with dispatcher servlet, standard servlet invocation model on Tomcat. What happens? We're trying to do a best effort adaptation of your Reactive Streams-based handler methods. We are taking Servlet 3.1 async IO streams, and we're building an adapter between your Reactive Streams publisher and the Servlet 3.1 async IO model. This is a quite special mode of operation on server containers, but they can do it. At least the latest generation of Tomcat, JD, and Undertow is quite happily processing, even in the async IO mode. It's a kind of mode of operation that you can switch a servlet request into. It's not an event loop-based setup, not a pure event loop-based setup. It's still a server container with a servlet invocation model, but it can handle Reactive Streams-based endpoint methods. So there's quite a bit of gray in between as well here. And this is in particular going back to this notion of being able to use reactive APIs, like a reactive web client and a synchronous back pressure enabled reactive client API, to also use it on Spring MVC and get some benefits out of this. On Spring MVC we can, and on Servlet 3.1, we can even do some back pressure. We interact with the servlet async IO streams and not going to only call the next step in reactive processing when the streams are actually ready to accept further data into the buffer. So this is actually quite flexible. It can be mixed and matched in lots of ways. But let's get back into the pure mode of a pure reactive web stack. If you're building an embedded Netty-based event loop setup, you also have the option to programmatically register your endpoints. We have a model called WebFlexFN, or dubbed WebFlexFN. It's essentially router functions and handler functions, a programmatic representation of this processing logic. For an incoming request, matching this predicate, which is actually literally a request predicate implementation, we dispatch to a certain handler method. And for that other predicate, we dispatch to that other handler method. In Java 8 method references, we have a fixed signature that we need to adhere to. This is essentially the handler function interface. Server request coming in, server response going out. The purpose of those is the same as with the annotated equivalent. We get an incoming request, it's not processed yet, and we're not supposed to process it. We are supposed to build a Reactive Streams publisher capable of processing it. So, for example, for this one down here, we call a repository that is hopefully capable of Reactive Streams as well. And then we build an HTTP server response, we set the HTTP status, and we pass the so-called body publisher into it. So we kind of compose the HTTP response instructions. This is also quite visible here. We don't have flexible signatures here. It doesn't work with Java 8 method references. We have to take the programmatic server request API. We extract the path variable. We convert it to a long. Then we pass the outcome of that into the repository find by ID method, which is able to produce a mono of user for us. The repository is not shown here, right? The repository could be a custom repository against the Reactive Streams driver, or it could be a Spring Data reactive repository. So within the Spring Boot 2 umbrella and Spring Data K, reactive repositories adhere to those conventions already. And then we once again build a server response setter status passing the body publisher and the element type, because the publisher doesn't retain its generics information in Java. This is sort of the very to-the-face version of that code. There's also a slightly nicer arrangement, the exact same code, slightly different structure, embedded lambda expressions with an incoming predicate matching and an embedded lambda expression containing the code that composes the server response. We don't see the signatures here. We only refer to the incoming argument as request, and we are supposed to return a server response here. So this is probably nicer to the average eye, right? And it's also a little more DSL style. We also have a Kotlin equivalent of this, a Kotlin routing DSL that's basically complying with the same kind of structure as well. These functional registration models only work for the reactive web stack. They are very explicitly designed for embedded reactive web stacks as an alternative to the annotation-based model. The aforementioned web client is also a new API that we're shipping in Spring Framework 5. This is sort of REST template in a more modern incarnation, not kind of blocking the call until that other server returns a response to us, but rather specifying an HTTP interaction in a sort of fluent API. We get a representation of it in the form of a Reactive Streams publisher for a single element or for a stream of elements. And that publisher hasn't done any work yet, right? So we just composed what to do when we reach out to that other service and when the response comes back. We can now register a subscriber for this and kind of trigger processing, or we can pass it on. Like in a Spring MVC setup, or in a Spring Webflow setup in particular, where the signatures are already based on Reactive Streams publishers, you can build a web client interaction and simply immediately return it, or make it a part of your transformation arrangement. You call another HTTP-based service through the web client API, then you maybe transform some of the outcome a little, and then you pass it back as the body publisher for this requested you need to arrive at a response at here. So in a typical service arrangement, like microservice architecture, where one service, a facade service, calls some other services in the background maybe, whatever it is, this actually goes together really nicely. So we provide, in Spring Framework 5, we provide many pieces of the puzzle. In the end, it's, of course, your call to build an application architecture out of this and to kind of accept the compromises that go with it. The Reactive Web Client is a very essential part of this. The other essential part is, unfortunately, not in our hands. That's data store drivers. A pure reactive web stack and the reactive focus in your architecture really needs reactive data store interaction. And where we're at right now, we have quite a few reactive drivers for MongoDB, for Redis, for Couchbase, for Cassandra. And first attempts, early attempts for reactive interaction with relational databases. Looking forward to 2019, Spring Framework 5.1, Spring Framework 5.2 timeframe, we expect there to be some proper solutions for reactive interaction, at least with Postgres. And there's even a project at Oracle already running for quite a while. So there's a chance of getting at least a reactively usable driver for the Oracle database out of it. But those do not exist yet. For the time being, reactive architectures are kind of driven from the bottom up. If you have a reactive data store driver, try to expose its power throughout your web architecture. If you do not have a reactive data store driver, if you need to interact with a relational database through blocking APIs, like with JDBC and JPA, you're probably better off in the Spring MVC stack. And if you want to do a little bit of reactiveness, you can do that with the Spring MVC stack. With the aforementioned adaptation to Servlet 3.1 async streams, you can have an arrangement where most of your endpoints are traditional, but some of them build Reactive Streams publishers, maybe with web client interactions to other services. So there's lots of trade-offs that you can choose to accept in a certain fashion. All right. There's lots more to say. If you look at recent talks from our wider team, you'll find quite a few talks about reactive architectures. I highly recommend Rosten's talk on the choice of servlet versus reactive, imperative versus reactive architectures. So there's lots of content up on our YouTube channel, and it's even published on several channels from several conferences in the meantime. So if you're interested in that, by all means, check out some of the deeper dive talks that we did in the past year about this. Now, let me use my final few minutes for another change of topic, for very quick pointers. There's a few things that we have been doing in Spring Framework 5 that are kind of connected a little to some other efforts, but are perfectly individually usable and not mentioned that often. For example, we have a clean nullability arrangement throughout our entire code base. So the entire Spring Framework code base and many of the projects around it, they are all coming with explicit non-null API by default conventions now, and add nullable declarations for any parameter, any return type that deviates from that norm, right? So it's non-null by default, and nullable in an explicitly annotated form. This is very usable in terms of code validation. We run IntelliJ IDEA's inspections. This constant conditions and exceptions is really a really nice one. It's kind of telling you whether you made the right assumptions, whether in the flow of your of the calls throughout your APIs and throughout your implementations, whether you're always making the right assumptions about something being nullable or never being null in the first place. It goes both ways. It tells you when you potentially run into a null pointer exception. It also tells you when you unnecessarily check whether this thing is null or not, because it can never be null anyway. So this is really a really nice effect. It's also self-documenting. If you look at our Java doc or our source code, you see immediately in the method signatures of Spring APIs, say Bean Factory get Bean, or even the REST template APIs, those sorts of APIs, they all come with a strict suggestion of whether you're allowed to pass in null, or even more importantly, whether you will ever get null out of a call, which allows you to make assumptions about this in your code, and which allows it allows you to adopt the same conventions, run the same inspections, and they are all validated, cleanly validated against the Spring Framework APIs. We also do this for Kotlin. It's actually quite essential for Kotlin, because Kotlin has nullability in its type system, and the Kotlin compiler only allows you to assign the outcome of a method call to a non-null variable declaration. It only allows you to do this if nullability is cleanly defined. This is the main reason why we do this. The Kotlin compiler understands our nullability declarations and allows you to write code within the Kotlin type system as you expect it to, with very clean nullability from then onwards. A kind of representation of this is this little API called Object Provider that you can inject into an injection point for flexible interaction, for getting new instances of a certain bean in a flexible programmatic form. This is a Spring Framework 4.3 API. In Spring Framework 5, it comes in two flavors now. That's a good illustration for what we're doing. GetIfAvailable and GetIfUnique, those methods are basically nullable by design, right? You're saying GetIfAvailable, if it's there, give it to me, if not, return null. That's their design. And in Spring Framework 5, they are explicitly at nullable now. At the same time, we also exposed other methods, which are even nicer. We can, for example, say GetIfAvailable. If it's not available, give me the instance produced by this default supplier. Since we're always going to return an instance now, either the one in the container or the one from the default supplier, this is non-null in its return declaration. Or even more functional, if you're saying, Object Provider, if your instance is available, please call my Java util function consumer with that instance. Otherwise, don't do anything. That's even better. So it really goes nicely with functional API design. Clean nullability, variants with non-null return types, and functional style callback variants of quite a few APIs that are very essential in the Spring Container architecture. So a few further ones. There's data classes. Our data binding, this is the model that can take incoming request parameters or other kinds of properties and bind them to a target object, now naturally understands data class conventions. So it's historically based on setter methods, but if we find an instance, if you declare a target type that does not have a default constructor, we go into data class mode. We expect there to be a single primary constructor that we can resolve your parameters into. We call that constructor and build your immutable data class without making any assumptions about setter methods. You can adhere to those conventions in Java. Just program your class like this, design it like this, but it's in particular designed to go nicely with Kotlin data classes and with Lombok data classes because they both use the same conventions. A Kotlin data class is basically just this one line. It generates accesses, the fields equals hashcode toString from it in the Kotlin compiler. Lombok is a little different because you actually declare the fields and Lombok generates the constructor, right? And equals hashcode toString. They all adhere to the same runtime convention, and Spring Framework 5 now automatically understands that convention. So, a few bonus things. It's not all about reactive. We also gave an overhaul to some of our traditional asynchronous interaction APIs, in particular Task Scheduler, which now has Java.time-based variants, and it has a couple of monitoring APIs, which also materialize in Spring Boot as a scheduled tasks actuator endpoint now. We have some refinements at resource level, which is now upgraded to NIO2, so not necessarily based on input stream and output stream. You can also interact with readable and writable channels in the NIO2 model now. And last but not least, we have the components indexer, which is a kind of geared towards the annotation-based model, a way to optimize a class path scan, right? We have been talking about trying to avoid class path scans, but if you have a class path scanning setup in your Spring configuration, there's also a way to add a Spring components file to your jar files at build time. And when you bootstrap your application, we understand the class path scanning instructions. We look for Spring components files. If there's sufficient information in those pre-generated files in order to kind of find the right components for you, we don't even scan the jar files at all. So it's kind of a way to offload some of the class path scanning overhead to build time instead. All right, time is up so far. There's only actually one more that I had. Logging is finally a sane arrangement right now. So you might not notice, in particular in Spring Boot, but if you look at your class path layout, you'll find that finally there are no bridges anymore. There's a single central Spring managed commons logging bridge automatically adapting to log4j2, SLF4j, and Java util logging. No other bridges, no manual includes in your POMs, no manual excludes anymore. So we streamlined logging quite a bit, and this is an ongoing effort in Spring Framework 5.1. We're also revising our use of logging levels, so you'll get quite a different logging experience, not necessarily at info level, but we're trying to fine-tune our exposure at debug level. So if you're switching on debug level for the entire framework, we are trying to optimize the experience that you have in development with a lot of noise removed, a lot of noise moves down to trace level. So log refinements are actually an important mission that we're on towards Spring Framework 5.1. And Spring Framework 5.1 comes to you in the third quarter. Release candidate is planned for late July, and the GA release is planned for mid-September. So Spring Framework 5.1, the next fine-tuning iteration, is not far away at all. All right, that's everything I had for you today. Thanks for your attention. Sorry for starting late here. Effectively, we might have gone like 2 minutes over time, even from there. If there are any questions, I'm here, right? Just pick me up or catch me outside. I'm happy to take them. There's a talk coming up right now. If you find me at lunch, feel free to approach me. I'm happy to have any discussion around all of this. So thanks and enjoy the rest of the show.